You are welcome to SK Pass International College. Please kindly like this video, subscribe to the channel, share the video to your friends in other schools. We are still on periodic chemistry and we are going to continue with our lesson on this topic. Periodic chemistry is an interesting topic and today we are going to continue. So if you have not yet watched my previous video, kindly watch so you can get the understanding of the concept better. So in today's presentation, we are going to study some periodic trends on the periodic table. So this is the periodic table. We have so many versions. This is one of the versions. And these elements, just like we discussed in our previous lesson yesterday, these elements has been grouped into what we call column, vertical columns, and horizontal rows. The vertical columns is the vertical column arrangement of elements on the periodic table is what we term as group. And then the horizontal row arrangement of elements on the periodic table is what is termed period. So today we are going to look at some periodic variations on the periodic table and how to use this variation to solve questions. So let's move on. Let's focus on how these periodic trends occur on the periodic table. Please try to watch the video to the end so that you can understand the concept in a better manner. All right, so in today's discussion, basically, we are going to look at some trends on the periodic table. So if you pick the periodic table just like we demonstrated or we showed, we have the arrangements, what we call the vertical arrangements, or what we call the column arrangement. So this is vertical or column arrangement. So we have 18 groups. So this is how Dmitry Mendeleev, a Russian chemist, grouped the elements with the help of Henry Moseley. This is how they grouped the elements into what we call the modern periodic table. So we have group 1, group 2, group 3, group 4, group 5, 6, 7, 8, 9, 10, 11, 12. Come here, we have 13, 14, 15, 16, 17, and group 18. Okay, so these elements have been grouped such that we have what we call period 1, period 2, period 3. So this becomes our period 4. So we have period 4, period 5, period 6, we have period 7. So it's up to 7 periods. So basically, we have 18 groups and 7 periods. Now in today's presentation, there are certain key things we are going to look at, especially some behaviors of some of these elements in the various groups. So first of all, let's look at group 1 elements. Okay, hydrogen, although is here, but it's not part of the group 1 elements. We stated that yesterday in our presentation. So we have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So here we have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, we have argon. Here we have potassium, we have calcium, cadmium, titanium, vanadium, we have chromium, we have manganese, we have iron. So from here we have nickel, we have cobalt, we have nickel, we have copper, we have zinc. Okay, so let's focus on the main group elements. I want to say main group elements. We are referring to those in S block and those in P block are called main group elements. So let's focus. Our focus is going to be on the main group elements. So let's look at these groups. Under this we have potassium, we have rubidium, we have cesium, and we have francium. These are the main group elements which we are going to concentrate on. And when it comes to calcium, under calcium we have strontium, under strontium we have barium, under barium we have radium. So these are very important. We are going to look at them. So when it comes to this also, under this we have krypton, xenon, we have radon, and protein. Under this we have chlorine is here, so we have bromine, iodine, acetylene. Yes. So we are going to focus on some of these ones. So let me quickly complete the rest with the help of the periodic table. So here we have the gallium, indium, we have thallium, we have Ihonium. Okay. So from here we have germanium, we have tin, and under tin we have lead, Pb. You are familiar with this. And we have lead. So let's come to under phosphorus we have arsenic. Arsenic we have Sd. We have bismuth. And then we have mescobium. MC mescobium. Then under sulfur we have selenium. Selenium we have tellurium. We have polonium. And we have ivamurium, which is Lv. Okay, so these are the main focus. These are the main group elements. We are going to discuss them in details. So let's focus on the main group elements. Yesterday's presentation, we said this block is called the S block. This is called the P block. or the transition metals. This block is called the P block. So inside this we have inner transition elements, which we normally refer to as the F block. So in some of the periodic table, we see it has been brought down. So those that it has been brought down, we have from atomic number 57 to atomic number 71, which start from lanthanum to lutetium. So that is from 57 to 71. Those F block elements are called the lanthanoids or the lanthanides. Then we have from 89 to 103, which we call the actinium or the up to the lawrencium. So they are also called actinides or the actinoids. So with this F block, we have two divisions there. Okay. So today we are basically going to discuss some periodic trends. But before we move on to the periodic trends, I would like us to look at how these atomic numbers are derived. So we need to have a way, a trick that we can use to know the number of or the atomic numbers. So we are going to use some magic numbers. So let's use these magic numbers: 2, 8, 8, 18, 18, 1, 2, 3, 4, 5, 32, 32. So let's count: 1, 2, 3, 4, 5, 6, 7. We said that we have 7 periods. These are the 7 periods. So these magic numbers, what does it imply? It simply implies that when it comes to the first period, there are only 2 elements in the first period. So that's the meaning of these 2. What it implies is that when it comes to the second period, we have 8 elements. You can see from here: 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 elements there. When it comes to the third period, we have 8 elements in the third period: 1, 2, 3, 4, 5, 6, 7, 8. Now when we move on to the next period, which is the fourth period, we have 18 elements there. So let's look at the fourth period. 18 elements: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are 18 what? Elements. It repeats in that order. The next one will also give us 18. The followed or the sixth period will give us 32 because of the F block elements. When you add them, you get 32 elements there, then another 32. So what this implies, if you want to designate this with their shell numbers, which we have the K shell, L shell, M shell, N shell, O, P, and Q. These are the shell numbers. Designate shell numbers. So these are their corresponding shell numbers. Now, we would like to use these magic numbers to know the exact atomic numbers of all these. So that is what we are going to do. So I'll just have to know that of the transition metals, then it will help me to know the others. So let's look at the transition metals. We know that this is having atomic number 1, and the other one has 2. So this is a dinner thing. But after the first period, we can now say that since we have 2, which is the first shell, since we have 2 shells, when we want to proceed to the next shell, then I will just do 2, 1, 2. So 2 plus this one will give me 3. So that is the atomic number for lithium. So I know from this to the next shell or next period, we have 8 electrons there, or 8 elements. So we just have to add 8 to this 3. So 8 plus 3 will give me the atomic number of the next element. So 8 plus 3, which is 11. So between sodium is 11. Then it also implies that from here we have 8 elements here. So 8 plus 11 should give me the atomic number of this. And that gives us 19. So 19 plus the next one is 18, which gives us 37. So 37 plus the next one, which I think will give us 55, and this will give us 87. So you can see from this place clearly that we can use these magic numbers to know the what? Number of, or the atomic numbers of the various elements. So from here I can quickly say, if that's the case, if this is 3, then this will be 4, and this becomes 5, 6, 7, 8, 9, 10. After that I count to 11, this becomes 12, 13, 14, 15, 16, 17, 18. Then I will come to 19. So this is 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So automatically this becomes our 37 value. So 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54. So automatically this becomes our 55th. So 55, 56, in that order. So when you get to this stage, they are F log elements. So you have to add an extra element. Here we have not extended that. So when you do that, you also get these results. So this is how we can use these magic numbers to know the atomic numbers on the periodic table. After knowing this, there are certain periodic variations that we need to know. Periodic variations. So before we move on to the periodic variation, we need to also know some characteristics of some of these elements. In my previous video, we stated clearly that group 1 elements we call these group 1 elements alkali metals. So all group 1 members are called alkali metals. This is an exception. Hydrogen is all right there, but it's not part of the alkali metals. It does not have the properties of these alkali metals or a metal. It's not having a metallic property. So hydrogen is not part. So from here, lithium, sodium, potassium, rubidium, cesium, francium, these are called alkali metals. So they are called group 1. We'll look at some few features of these group 1 elements. Then let's come to group 2. These are also called alkaline earth metals. They are also called alkaline earth metals. So let's note that. Then we have a name for group 15 and 16, which I ask you to write your answers in the comment section. We'll come to that. But for now, we are going to concentrate on group 17. They also have a family name called halogens. Then we can also talk about group 18. We also have a family name we call the noble gases, or the inert gases, or the rare gases. So these are the family names. Now let's look at some few characteristics of these elements. Now when you pick these alkali metals are very reactive. Okay? They are very reactive. So one of the characteristics of these alkali metals on the periodic table, these alkali metals are very reactive. So these alkali metals can react with some reactive metals. For instance, let's assume we pick an alkali metal like sodium, try to react with any this reactive metal trying to react with ACl or an acid. So we are going to form sodium chloride, and then there will be a gas which will be released, which is called hydrogen gas. So you can see from here that anytime any of these reactive metals reacts with an acid, a gas is evolved. And that gas can be referred to as hydrogen gas. This gas can be tested when you send the gas closer to a glowing slate. You hear a pump sound indicating that there is hydrogen gas present. So these are some of their properties. We can also say that these group members, they are soft metals. They are soft metals. Why are they soft? They all lose one electron. They are outermost electrons, so they all have NS1 when you want to write the electronic configurations. For instance, if I'm writing that of lithium, atomic number 3, we are going to have the outermost, we just want to write the outermost electron. We are going to have 2s1 for lithium. When we want to write that of sodium, we are going to get 3s1 for sodium. Potassium will have 4s1. When you go to rubidium, that will have 5s1. When you go to cesium, that will have 6s1. When you go to francium, that will have 7s1. So you can see clearly that they all have their outermost electron having 111 electron each. So that is why they are all belonging to this group. And in my previous video, I explained that anytime you see the principal quantum number, the principal quantum number will tell you the exact period that element is located. So with this principal quantum number, 5s1, I can predict from this principal quantum number that the element will be in the 5th period. So you can see rubidium is in the 5th period. If I pick a principal quantum number like 7s1, it indicates that the element is supposed to be in period what? Supposed to be in period 7, group 1, and block S. That is the thing. So outermost electrons are very important. We need to appreciate when we are writing outermost electrons because we use them in so many things. Alright, so these are some few characteristics they possess. Now most of these elements, they react with the non-metals in terms of their reactivity. Most of them react with the non-metals to form ionic compounds, except beryllium. Okay, we have not gotten to beryllium yet, so beryllium is in group 2. So most of these elements will react. So for instance, let's assume I have I can have any of these reacting with any of the non-metals like chlorine to form halide salt. So it has formed an ionic halide, which is a salt here. So you can see from here, this is from group 1 reacting with any of the non-metals. Now form this halide, this salt. Can form something like this, reacting with any of the non-metals here to form potassium oxide. So from here, you can see clearly that this is 2. So let me bring 2 here. And this is 2 here. So if I bring 2 here, there's no place becomes 4. So you can see from here that this is a reactive metal from the group 1 reacting with a non-metal, and it has formed this oxide. So they react to form oxides, basic oxides. So these are some of their reactivity. Now when it comes to group 2, they also have similar properties to that of the first group. Now when you pick the second group, for instance, the element there, beryllium, magnesium, calcium, strontium. When you also want to write their outermost electron, for instance, beryllium, to have 2s2. When you move on to the next element there, magnesium, we'll have 3s2. The next element there, calcium, the outermost electron will have 4s2. When you move to the next state, strontium, to have 5s2. When you move to the next one, barium, to have 6s2. And when you move to radium, to also have 7s2. So you can see they all have ns2 as their outermost electron. Now, when you look at this, we are saying that these elements are soft elements. But when you compare the alkali metals to the alkaline earth metals, we can say that the alkaline earth metals are harder than the alkali metals. Why? Because these elements lose 2 electrons. Okay, so we are going to look at some periodic variation to get the concept to work. So that is the concept. Alright, now let's now move on to another interesting aspect on the periodic table, which we refer to as periodic variation. But before we move to periodic variation, there is one thing we need to know about these d block elements, which we call the transition elements. Now, when you pick the transition elements, they have some similar characteristics, and when you pick the halogens, they have some characteristics. For halogens, most of them are very reactive. See, they are more electronegative, and so they are normally used to form so many halides. Okay, so if you look at this, you have fluorine, which forms fluoride. So all these the elements here, most of them are diatomic. So look at an element like fluorine, it can form diatomic F2. Look at chlorine, can form C2. We look at bromine, can form Br2. Ionic can form I2. These elements cannot form. So aspartame is not diatomic. Now there are some few things you need to know about the group 17 elements. Now naturally, this fluorine is existing as a gas. As it moves down, this fluorine naturally exists as a gas. But when you move down, there is bromine. This bromine exists naturally as a liquid. So whilst we go in chemistry, we're doing organic chemistry, we shall be doing some tests on unsaturated hydrocarbons. How to test for unsaturation in hydrocarbons by using bromine water. When you do that test, you see the bromine water will have to decolorize the solution. So when you get to organic chemistry, we're going to talk about this bromine water utilizers, how it is used. Now when you come down, this iodine becomes solid. So as you are moving down, they have some variations on the periodic table, which we'll look at. So that is one thing we need to know about this. Now when it comes to the group 18 elements, they are called the noble or the real gases, or the inert gases. These type of elements, they do not react. Most of them are unreactive. Few of them do react, but most of them are unreactive. Why? Because they are stable in nature. Therefore, they do not prefer to react. But few of them are reactive. So we will look at some of these elements which are reactive. Post your answer in the comment section and tell me the element among these which is highly reactive and why it is so. Alright, so that is for the general groups. Now when it comes to the D block, one thing we need to know about the D block element is that we have the D block and the F block. So let me quickly talk about the D block. For D block elements, most of them have what we call variable oxidation state. So we are asked to write some characteristics of transition metals or D block element. Characteristics. So some of the elements have variable oxidation state. Some some of these elements are variable in this state. And when you want to check, for instance, this copper, we have copper 1 and copper 2. So we can form a compound out of that. Let's say you have this. This is copper 1 oxide and this is copper 2 oxide. So you can see this copper has variable oxidation state. So it's one of the properties of big log elements. Another property we can talk about, we can say they are paramagnetic. Now when you are filling the D block elements, we fill, some of them are filled partially. The D block normally they are filled partially or half filled. So we are saying that these D block elements are paramagnetic in nature. And some of the elements form colored compounds. They form colored compounds. So when you are doing qualitative analysis, you shall be looking at the colors of some of these elements, and when you react them with some reagents in excess and in drugs, what happens to their solubility? At times the color, the precipitate form will tell you the kind of metal present. So that is what we'll be looking at that when you get to solubility to understand the concept better. So these are some few properties of these transition metals. There are more of them. You can do research and add few. Alright, now we have inner transition metal, which we call the F block elements. When you pick the F block elements, the elements there, most of them are catalytic, meaning we normally use most of them as catalysts. And when we talk of catalysts, these elements are normally used to speed up reactions. So that is basically what you have to do. Alright, now we want to look at trends on the periodic table, which we call periodic variation or periodic trends. When we pick the periodic table, we have some periodic variations or periodic trends. And when we talk of periodic variation or trends, these elements which have been arranged have some physical and chemical properties they exhibit when they increase in their atomic numbers. So when we are moving down the group, you can see the atomic numbers are being increased. From 1 we move to 3, from 3 we move to 11 to 19 to 37 to 55 to 87. So you can see there is variation or there is increment in the atomic numbers. When you want to move from left to right on the periodic table, for instance, sodium, magnesium, aluminum, you can see from 11 we move to 12 to 13 to 14. So why is this movement is occurring on the periodic table? There are some physical and chemical variations. And so these physical and chemical variations on the periodic table is what is termed as periodic variations or periodic trends. We have some few periodic variations and trends which we need to understand very well. This video, we will talk about maybe 2 of them and talk about the other ones in our next video. So let's look at some periodic variations on the periodic table. The very first one we would like to talk about is what we call atomic radius, or someone will say atomic size. So this is one of the variations. We also have another variation called ionic size or ionic radius. We can also have another type of variation called ionization enthalpy, or you can say ionization energy, or better still, you can say ionization potential. it means the same. So when you're asked to define ionization potential, it's the same as defining ionization enthalpy or ionization energy. So it's one of the variations. We also have another variation which we'll talk about. We have what we call electron affinity. We are missing the physical and the chemical. We will explain them one after the other, and we'll decide which ones are chemical variations and which ones are physical variations. So electron affinity. Then we can also talk about electronegativity. Then we have another one called electron configuration. Writing of the electronic configuration or electron configuration also affects the periodic variation. So electron configuration. We can have another one. Boiling point. We can have melting point. Then we can have atomization. And so on and so forth. There are some few. So all these are periodic variations on the periodic table, which we need to understand. But there are some important ones we would like to talk about in today's. We can also talk about, let me add the last one, the density. So all these are periodic variations or periodic trends on the periodic table. Let's quickly look at how these periodic variations affect the elements on the periodic table. So let's start with the first type, which we call atomic radius or atomic size, the same thing. Now, when we talk of atomic radius or atomic size, just like the concept you have studied in mathematics, look at this. In mathematics, we have been taught if you have a circle, this is called the circumference, and we have what we call the center of the circle. And in mathematics, we have been taught that anytime we have a line drawn from the center of this circle to meet the circumference, that line is called radius. So when I have another line meeting from this point center to meet this circumference, it's called radius. So from this, we can say 2 radii will give us diameter. Since 2 radii is equivalent to diameter, what it implies is that if I want radius, then radius is equal to divide this by 2, divide this by 2. You get diameter over 2. So radius is equal to, when you divide the diameter into 2, you get the radius. That is the concept. Now we are going to transfer that knowledge to chemistry. And the concept chemistry brought about this theory anyway. So let's now bring this concept into existence. I want to pick an atom. When you pick an atom, we have what we call the nucleus. Okay, so that is the center we are referring to in a second as the nucleus. Around the nucleus, you have shells. So this is a shell, this is another shell, this is another shell. So as the shells are growing, the size of the atom is becoming bigger. So what is termed in mathematics as circumference is the outermost electron, the last one. That is what we call the valence electrons or the outermost electron. So this outermost shell is what we refer to in mathematics as circumference. Now, anytime I have a distance looking at this, the center, distance that moves from the nucleus to the outermost shell, that distance covered from the nucleus of an atom to the outermost cell of that atom is called the atomic radius. So when you say atomic radius, in a very simple manner, you can say it is the distance covered from the nucleus to the outermost shell of an atom. That distance covered is what we refer to as atomic radius. But we have so many types of atomic radius, and therefore, because of the types of atomic radius, we have been able to get some different definitions for atomic radius. But this is a generalized meaning of atomic radius. So let's look at the types of atomic radius and how it affects the size of atoms on the periodic table, the variations on the periodic table. Sorry. So let's look at this types of atomic radius. The very first type we'll talk about is called covalent radius or covalent atomic radius. Okay, so that is the first type. Now, in covalent atomic radius, it is formed like this. We have two identical atoms. So let's use hydrogen for a case study. Hydrogen, hydrogen. We know hydrogen will donate one electron here, another one also donate one. They share to form a covalent bond. So with this hydrogen, the atoms here are identical. So what is happening here is I have the nucleus of the atom here, another nucleus here. Now there is a distance from here to here becomes the radius, and from the distance from here to here to becomes another radius. So if you join these two like this, it means what it implies is that from this line, from here to this circle forms a radius, and from this part of the circle to this part also forms another radius. In between the two, we call that diameter. So from here, you can see that in atomic radius definition, we can say it is half the distance. Look at this, half, because this is the distance from here to here. There is a distance here, so half the distance between the nuclei of two closest atom in a substance. So half the distance between the nuclei of two closest atom in a substance is called atomic radius. Half the distance between, look at this, half the distance. So this, from here to here we have radius. From here to here we have another radius. So we have to divide this so that we get a radius. So half the distance between the nuclei, so plural form of nucleus, as nuclei, have the distance between the nuclei of two closest atoms in a substance is what we call atomic radii. But when you want to define this in covalent radius, if you are asked to define covalent radius, then you be specific enough to say it is half the distance. Look at this, it is half the distance between two identical atoms in a single covalent bond or in a covalent bond. So here you are specific to a covalent bond. So it depends on the type of what covalent bond and the definition you give. So in this case, it is just the same definition, just that we are bringing in covalent bonds. So half the distance between the nuclei of two identical or two closest atoms in a covalent bond is termed covalent radius. So this is one type of atomic radius. We also have another type of atomic radius, which is known as ionic radius. Ionic radius. So with ionic radius, one thing we need to know about ionic radius is, look at this turn around, this is what is going to happen. Now in this ionic radius, you can see the atoms have been combined, but they are not identical, they don't look alike. One is somehow bigger than the other. So in this case, this is the nucleus, positively charged, this is the nucleus positively charged. So we can also have the distance moving from this place, okay, from here to here, it forms a radius. Then the distance from here to here forms another radius. So in between these forms the diameter. So in this case, it's the same definition. The distance moved from here to here is the radius of this circle, and then the distance moved from here to here is also the radius of the other circle, or the other atom. We are using atoms, not circles. Okay, so from here, you can predict or you can say that this also have the distance, okay, but these atoms are not identical. So in this covalent ionic radius, or this type of atomic radius occurs in ionic radius. So we have to note the difference between the structure or the drawing of covalent radius and that of ionic radius. The difference is in covalent radius, the sizes are the same. So this is another type of atomic radius. Let's look at the next type of atomic radius. We can also have the third type known as metallic radius. With metallic radius, let's look at how it looks like. Sorry. Metallic radius want to worry in a bit. My time, I get it. This time around, I'm getting it. Okay. So here, in metallic radius, there's no overlap. There are two atoms, they do not overlap each other. So it's like this. So you can see, although they are identical, but they are not overlapping. So this is called metallic radius. So in this case, this is my nucleus of this atom, this is the nucleus of this atom. Have the distance moved. Okay. So from here we have the radius and then another radius forming the diameter in between the two. So have the distance between the nuclei of two closest atoms in a metallic crystal is termed as metallic radius. So here when you are defining metallic radius, you need to be specific that have the distance between the nuclei of an atom, okay, two identical atoms is in a metallic crystal. In a metallic crystal is the term or is termed metallic radius. So these are the types of radius we need to know and how they look like, how the sketch goes. So that is basically what I can say about metallic radius. Now, atomic radius is normally measured in picometers or nanometers. Picometers here or nanometers. And at times we can also use the nuclear magnetic resonance, NMR, to also determine, or microscopy to determine the atomic radius. The reason why atomic radius is not easily discovered or cannot easily be measured is because the atoms have a very small size. We say when you are defining an atom, we say the smallest particle of an element, which can take part in a chemical reaction. So because they are very small, it's not easy to know the radius of the atom. So we use some specific instrument to determine the radius. Now let's look at the main variation occurring in this atomic radius. Look at this. When I'm moving down the groove, that is from top to bottom, we are going to look at the trends of atomic radius. There are two main things affect the size of an atom. The two main things that affect the size of an atom is called shielding effect or screening effect. Either you say shielding effects or screening effects. That is one thing that affects the size of an atom. And the second thing that affects the size of an atom is called effective nuclear charge. Effective nuclear charge. So these are the two main things that affect the size of an atom. So let's look at how this is done. Now when you are moving down the groove, okay, when I'm moving from top to bottom of the periodic table, look at what happens to the atomic size. So let's take lithium, for instance, lithium. So this is my nucleus, okay, this is my nucleus. The first shell will pick 2 electrons, and then this will pick 1. So this is lithium atom. Now let's move on to the next one. This is my nucleus. The first will pick 2, and next will pick 8, 2, 4, 6, 8. And then the next will pick 1. This is sodium atom. Excuse me. Let's look at the next one. I have my nucleus. The first shell picks 2. Next one will pick 8, 2, 4, 6, 8. Next one picks 8, 2, 4, 6, 8. Next one will pick 1. So this is my potassium atom. Now let's use this as a case study. Once you move down the groove, there is something happening. Now you realize that from lithium to sodium, we added another shell. So while you're moving down, we are adding extra shells. So 3 shells in this period, 2 shells here. So while you move down, the number of shells increases, therefore increasing the size of an atom. And anytime the number of shells increases, we call that shielding effect. Or if you look at it in terms of screen, if it is a TV screen that we are buying, you can see this screen is becoming big, the screen is becoming big. So you can see from here, we move to a different screen, the screen is becoming bigger. We move down, the screen is becoming bigger. Now when we move down to the rubidium, the screen will become bigger than that of potassium. So what it means is that when you are moving down the group from top to bottom on the periodic table, the atomic size increases. The reason is because the shielding or the shielding effect increases. Because the atoms enter into new orbitals or new shells, therefore increasing the size of the atom. These are some reasons you need to know. So that is the reason, and that is what happens when you are moving down the group. Now let's come to moving from left to right on the periodic table. But before we move there, let me explain this concept very well. When you say moving down the group, that is from top to bottom. You know the size of the atom increases. Increases means from the smallest to the highest. Increases means from the smallest to the highest. So in this case, you can see lithium is smaller than sodium, and lithium is smaller than sodium. Sodium is also smaller than potassium. Potassium is smaller than rubidium. So when you want to move like this, it means the biggest starts all the way. From here, cesium is bigger than rubidium is bigger than this. So this becomes the smallest. So that is the meaning of its increases. Alright. Now, let's look at when we are moving from left to right on the periodic table. I'm using the word left to right. But when I say moving across the period, I can also move from right to left. That is across the period. So we need to be specific here. And when I say moving down the book, it is from top to bottom. But I can ask you, moving from bottom to top on the periodic table. Moving from bottom to top means I'm moving from here to top. In this case, what happens to atomic size? Post your answer in the comment section. When you're moving from bottom to top on the periodic table, what happens to atomic size? Post your answer in the comment section. Alright, you can pause your video and post your answer. Yes. What are you getting? So you can see when I'm moving from what? Bottom to top of the periodic table, what is happening to atomic size? Atomic size decreases. Decreases mean from the highest to the smallest. So whilst I'm moving from bottom to top on the periodic table, atomic size decreases. But whilst I move from top to bottom or down the group like this, atomic size increases from the smallest to the biggest. Take note of that. Now let's talk about moving from left to right on the periodic table. What happens to the atomic size? Now whilst I'm moving from left to right, let's look at a typical example like sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. Let's exempt argon because these elements are stable enough. So let's exempt them. Now, what is happening here is called effective nuclear charge. When I say effective nuclear charge, when you pick the atom has a nucleus. And the nucleus is positively charged because inside the nucleus we have protons and neutrons. Since the neutrons have no charge and protons are positively charged, it implies that the nucleus as a whole is positively charged. So what you are going to do here is that when you pick sodium, you ask yourself, how many protons are in sodium? We have 11 protons. So it means this 11 is positively charged. 11 plus, we have 12 plus, we have 13 plus, 14 plus, 15 plus, 16 plus, 17 plus. So these are the nuclear charges. The nucleus is positively charged, so these are the charges in the nucleus. Now, let's look at how sodium atom looks like. This is sodium. We have 2 electrons, 2, 4, 6, 8. Then there's outermost electron. Now this one, they all have the same, when you draw, they all have the same shell numbers because they are in the same period. Look at magnesium. This is the nucleus. This will pick 2, 2, 4, 6, 8. But this, the outermost electron, they are not, one is not bigger than the other in terms of the shell. They have the same number of shells. So, but this, what is happening here is, this has 2 electrons. So it continues like that. Now, since the protons are positively charged, and electrons are also negatively charged. Now, there's 1 electron here, and there are some protons here. So this electron will try to pull itself towards the nucleus. Whilst it is pulling itself towards the nucleus, it is making the atom smaller. But look at this, it has only 1 electron. These are called core electrons, and it has 1 outermost electron, and it's pulling. Now the nuclear charge here is 11. Now let's come to here. Now this one is having 12 at each nuclear charge. So, and it has 2 electrons. So you can see that actually here is going to be more because there are more of the electrons which will try to pull towards the nucleus because the nucleus is positive. And the charge here, the nuclear charge here is also greater. So they will pull more and it will make the atom, the size of this atom become smaller than that of this. So actually, in actual sense, what is happening here is anytime the nuclear or the number of protons increases, it increases the nuclear charge. And the greater the nuclear charge, the smaller the size of the atom. So when you look through this, which one has the greatest nuclear charge? You can see it is chlorine. Chlorine has the greatest nuclear charge. Therefore, we can say chlorine is the smallest among these elements. So when you are moving from left to right, look at this. From left to right, sodium, magnesium, it means the atomic size, what is happening to the atomic size? It is decreasing. Decreasing means from the biggest to the smallest. So, in actual sense, sodium is bigger in size than magnesium, and magnesium is bigger in size than aluminium. Aluminium is bigger in size than silicon. Silicon is bigger in size than phosphorus. Phosphorus is bigger in size than sulfur, and sulfur is bigger in size than chlorine. So it means, moving from left to right on this periodic table, it means chlorine is the smallest here. So the bigger the atomic size, the smaller, the bigger the nuclear charge, the smaller the atom. So that is what we need to understand from here. So moving from left to right on the periodic table, what happens to atomic size? It decreases from the biggest to the smallest. So this is having the smallest size. But what will happen if I'm moving from right to left on the periodic table? What will happen to atomic size? In this case, we say it will increase, meaning from the smallest to the biggest. So take note of how persons are asked on this. It can be that they will ask you to arrange the elements, moving from what? Right to left. When I give you question, moving from right to left, what happens to atomic size? In this case, you don't say to decrease, but to rather increase. But once I'm moving from this right to left, the size of the atom is becoming bigger, because this is the biggest. But once I move like this, it is decreasing. So take note of that. And the main thing that is causing the size to decrease is called the effective nuclear charge. Effective nuclear charge is the net positive charge surrounding this. So this is the net positive charge in this nucleus. So this net positive charge in the nucleus is causing the atom to be smaller in size. So the bigger the effective nuclear charge, the smaller the size of the atom. The smaller the effective nuclear charge, the bigger the size of the atom. So the arrangement above. So I can ask you to arrange the following in increasing atomic size, given reasons. So I can mix them up. I can bring aluminium, I can bring sulfur here, I can bring silicon here, okay. I can bring magnesium here. So in this case, the only thing you need to know, if something like this is given to you to arrange, the only thing you need to know is to know the atomic numbers or the proton numbers. We know aluminum is 13, and silicon, this is sulfur, so sulfur is 16, silicon is 14, and magnesium is 12. So you just have to know these are protons, and protons are positive charged, so they are having plus plus plus. So which one has the highest proton number here? And from here we can attest to the fact that this has the highest. And we are saying the bigger the effective nuclear charge, the smaller. So this is the smallest. Followed by, from 16, I'll move to 14. Followed by silicon. Followed by aluminium. So it means that magnesium is the biggest among these arrangements. So that is how we do the arrangement. And to end this video, I'll talk about the last periodic variation, solve more questions to get the concept better. Now let's talk about this last periodic variation, and we'll continue with the other periodic variation in my next video. I will continue with the rest of the periodic variations in my next video. Try to watch the video till the end. Share and comment if you don't understand anything. Now let's look at the last or the next periodic variation. We would like to look at ionic radius or ionic size. Now anytime we talk about ionic radius, it is just similar to atomic radius, but there are some few variations. Now let's look at a typical example of an ion. When I have this sodium ion, this becomes sodium plus. So this is sodium ion. This fluorine minus becomes fluorine ion. Let's have another ion like oxygen minus 2. Let's have another like magnesium 2 plus. Let's have another one like aluminum 3 plus. These are all ions. Okay, so an ion is an electrically charged atom. So anytime the atom is having a charge, we call that ion, so ionic size. But the concept I want to develop here, I'm going to mix some atoms to that. So let's pick something like neon. Neon is not charged. Now, we are going to develop, or we are going to determine something out of this. If I want to know how many protons are in sodium plus, we have sodium has 11, so 11 plus. We are only looking at the protons first. Fluorine has atomic number 9, so it has 9 plus. This oxygen is having 8 plus. Magnesium has 12 plus. Aluminum has 13 plus. Neon has 10 plus. These are called proton numbers. So this is the proton numbers of the respective species. Now let's look at the number of electrons they have. So from here, sodium plus will have, sodium was having 11, it has lost 1 electron, so it's now having 10 electrons. Fluorine was having 9, it has gained 1, so it's now having 10 electrons. Oxygen was having 8, it has gained 2 more, so it's now 10 electrons. Magnesium was having 12, it has lost 2, it is now 10 electrons. Aluminum 3 plus was having 13, it has lost 3, so it's now 10 electrons. Neon is still 10 electrons. Nothing has been done to it. Now you can attest to the fact that all these species are having the same number of electrons. So anytime we meet a case like this, we call this isoelectronic species. So these species are referred to as isoelectronic species. So how do we put these isoelectronic species? We can define isoelectronic species as isoelectronic species are series containing ions and atoms with the same number of electrons. I repeat, isoelectronic species, isoelectronic species are series containing ions. When I say ions, can be cations and anions. That is cations and anions, and atoms with the same number of electrons. So the emphasis is on the same number of electrons. So any species or any series containing ions and atoms. Ions mean they can be cations and anions, just like this. We have some cation, this is a cation, this is an anion, cation. So it's a mixture of ions, that is cations and anions, and atoms having the same number of electrons. That species is determined or is termed isoelectronic species. So the first thing we can see from here is the species above is an isoelectronic species. That is the first thing. Your ability to identify that will help you a lot. But we can ask you to arrange the following in increasing ionic size or decreasing ionic size. Now, how do you arrange this in increasing ionic size? Here we are dealing with the ions. So if you want to arrange this in increasing ionic size, we've just established a fact that anytime you have a higher nuclear charge, you are the smallest. So you just glance through quickly. Look at the one with the highest nuclear charge. So when you check through, we can see that aluminum has the highest nuclear charge, 13 plus. So aluminum is the smallest. So from here, we want to arrange in increasing ionic size. Increasing means from the smallest to the biggest. So let's look at the smallest. We have aluminum 3 plus is the smallest, followed by the next one with the biggest effective nuclear charge. So from 13, we have the next biggest to be this, 12. So we have magnesium 2 plus, followed by the next. From 12, we have 11. So we have sodium plus. When we leave sodium plus, the next one, 11, we have 10. It's neon. From 10, we have 9. So F minus. From 9, we have 8. So oxygen minus 2. Let me add another one. N minus 3. This one will have 10 electrons as well, because it is having 7. It has gained 3, so 10. But the number of, let me use, the number of this is 7 plus. Nitrogen is 7, so 7 plus, it has 10 electrons. So when you want to add nitrogen minus, then that will become the biggest. So you can see what I've done. This arrangement is called increasing ionic size. Increasing means from the smallest to the biggest. So it means N minus 3 is the biggest in terms of size. So this is how the arrangement is done. If you are asked to arrange the following in increasing ionic size, given reason. In your reason, you have to state that this species, the species above, is an isoelectronic species because they have the same number of electrons to get a mark for that. Explain that to get a mark. So before you meet any person like this which is isoelectronic, first of all state in your reason that the species above is an isoelectronic species because they have the same number of electrons, and that is what you can see from there. Now after saying that, you tell us the greater the nuclear charge, the smaller the size of the atom. So if you check through, since aluminum has the greatest nuclear charge and nitrogen has the smallest nuclear charge, the arrangement above. So this arrangement above indicates that this aluminum 3 plus has the highest nuclear charge, which is 13, and then this nitrogen minus 3 has the smallest nuclear charge. So that is the concept, and that is how you explain this point. So this is for isoelectronic species. You can also be given something like this. Let's give this example, then we draw curtains on this presentation. Now, let's assume I have species like this. Cl minus, S minus 2, calcium 2 plus, K plus, then I have Ar. Okay, so we can also ask you to arrange the following in either decreasing or increasing. So this time around, let's arrange it in decreasing ionic size. Decreasing means from the highest to the lowest. So with this, the first thing you do is to first of all check for the nuclear charges. So chlorine is having 17 plus, sulfur is having 16 plus, calcium has 20 plus, potassium has 19 plus, and this has 18 plus. Argon. After checking the nuclear charge, you come and confirm whether they have the same number of electrons before you can conclude that they are isoelectronic. So from here, chlorine was having 17, it has gained 1, so it's now 18 electrons. Sulfur was having 16, it has gained 2, it is now having 18 electrons. Calcium was having 20, it has lost 2, it is now having 18 electrons. Potassium was having 19, it has lost 1, it is now having 18 electrons. Argon is still having its 18 electrons on top. So this is what you are supposed to do. Your ability to do this will tell you, will let you know that this species is an isoelectronic species. So from here, you can attest to the fact that this is an isoelectronic species because they are all having the same number of electrons. But how do you determine the size of this ionic species? So let's come back. The bigger the number, the bigger the nuclear charge, the smallest the smaller it will become. So which one has the biggest nuclear charge? it is calcium 2 plus. So look at this. So if I want to arrange this in decreasing means from the highest. So which one will be the one having the least nuclear charge? That will be the one very big in size. So from here we have X minus 2 followed by Cl minus followed by argon 18 followed by K plus followed by calcium 2 plus. This is decreasing. Ionic size. So this is decreasing ionic size. In this case, this is the biggest and this is the smallest in terms of size. Decreasing means from the highest to the smallest. So this S minus 2 is the biggest and this calcium 2 plus is the smallest. Now if you don't really understand the nuclear charge explanation, all that I can say is, let me come back to a normalized situation. For instance, let's assume this chlorine was having 17 as a value, 17 oranges. Okay? This sulfur was having 16 oranges. This calcium was having 20 oranges. This potassium has 19 oranges. This iron has 18 oranges. Then, the following day, something happened. We went back to check. Now, this chlorine having 17 is now having 18 electrons or oranges. This sulfur having 16 is now having 18. So, between these two, who has really increased? We can classify or clarify that this amount between these two, we can say that the one that has really increased is this 16 because you were having 17, you have only increased in 1. Okay, you have only increased in 1. But this was having 16, it has increased in 2, so this has increased. So this is bigger than that. Now let's come here. This one initially was having 20 oranges, but the following day it had 18, so this has reduced. It has really reduced 2 more oranges, so it's now becoming so small because the actual size has reduced. When it comes to potassium plus, this was having 19 and it has also what? Reduced to 18, so this has also reduced. But when you compare these two people, this man has reduced than this because this was having 19, just reducing in 1. This has reduced in 2. But when you pick this one, nothing has really happened to it because it was having 18. It is still having 18, so the value remains the same. So when you want to really check the one who has really benefited from the whole process, you can say it's S minus 2 because it has increased in 2. This has increased in 1. This was having its original value, and this has only reduced in 1, but this is the person who has been affected the most. And that is the concept. Thank you for watching this video. Please kindly like the video, share to your friends, comment, and let's have a wonderful lesson in our next presentation. Do not miss the next presentation. Therefore, if you have not yet subscribed to the channel, I'm urging you to subscribe to the channel. Thank you and see you in my next presentation. Bye bye for now.